spectroscopic method. So in the previous 6 units, we have discussed the molecular spectroscopy technique, and this one is the atomic spectroscopic method. So first we will start the origin and classification of the different atomic spectroscopic methods.
Sir, you are not audible.
Yes. So this one is the origin of atomic spectrum. First, we will discuss the origin of atomic spectrum, because we know that an atom contains set of quantized energy levels. In an atom, the electrons are present in the various quantized energy levels, and the energy level with minimum energy is called the ground state, while the higher energy levels are referred as excited state. Further, the electron in an energy level can undergo a transition to another level of a higher energy by absorbing a photon of appropriate energy equal to the difference of the energy of the two levels. On the other hand, the transition of an electron from higher energy level to a level of lower energy level is accompanied by and emission of the difference in energy from a radiation of appropriate wavelength. A spread of wavelengths of the photon, a spread of wavelengths of the photon absorbed or emitted versus their intensity is called a spectrum. That means the number of electrons present in an atom, if you consider an atom, the number of electrons are present in various quantized energy levels. So the energy levels with minimum energy level, the energy levels with minimum energy are called as the ground state, while the higher energy are referred as excited state. So when one atom will be excited by observing different electromagnetic radiations or any other different technique, if the atom will be excited, then the electron will move from the ground state to excited state, and it will move to which excited state, that depends upon the amount of energy absorbed. And after that, in the excited state, the lifetime of the electron will be very less, and again that will come back to the ground state by emitting electromagnetic radiation, and the process is called as emission. Now coming to the classification of different atomic spectroscopic methods. The atomic spectroscopy, in atomic spectroscopy, the element present in the sample are converted into gaseous atoms or elementary ions in the process that is called atomization. So in order to observe atomic spectroscopy, first the element present in the sample will be converted into isolated gaseous atoms or elementary ions, and the initial process is called as atomization. This process, the process of atomization, can be classified, can be done in various ways. For example, that can be done using a flame or electrothermal method, or by using a furnace, or the third one is by inductively coupled argon plasma, or the next one is direct current argon plasma, or the next one is electric arc. So these are the various process of atomization. In order to observe the atomic spectroscopy, first the elements present in the sample should be converted into gaseous atoms or elementary ions. That process is called atomization. The atomization can be takes place by these various methods. These methods accomplish the atomization process in different temperature ranges. One of the vapor phase, the atoms of the element interact with the radiation and provide information about the different atoms present in the sample. The interaction of the radiation and the matter can be manifest itself in terms of absorption, emission, and fluorescence emission. Accordingly, we have atomic absorption, emission, or fluorescence spectroscopy. That means the electromagnetic So radiation can be interact with the matter so that will undergo either absorption, emission or fluorescence emission. So that's why the corresponding spectroscopy of the atomic spectroscopy, that is called atomic absorption spectroscopy AAS, and another one is atomic emission spectroscopy, that is AES, and the third one is atomic fluorescence spectroscopy, that is AFS. First we'll discuss about the AAS. So in this method, the atomic vapor containing free atoms, that means isolated gaseous atoms of an element in the ground state, are subjected to UV visible radiation source emitting a characteristic frequency of the element present in the atomic vapor. That means different atoms will, so when the sample containing isolated gaseous atoms or the sample containing free atoms of an element in the ground state are subjected to UV visible radiation, initially the atoms present in the sample first excited by irradiation of UV visible radiation, so that by a particular UV visible source, and after that the electrons present in the atom, they will go to the excited state, and again they will come back emitting electromagnetic radiation of a particular characteristic frequency, and by analyzing that emission spectra we can know the different atoms present in the sample. The radiation is observed and the intensity of the radiation is attenuated. The observed radiation cause excitation. That means initially the sample will undergo excitation by UV visible source. The
Sir,
observed, hello,
sir,
hello.
sir, sir. This is Devashish Pati.
Yes, yes.
Sir, ये जो सब equipments एगुड़ा सब practical हमर हबो की?
हाँ, ये सुनो तमरो थ्योरी सरी साइला परे जो
आगे
अच्छी डिफरेंट ସବୁ ପେପରର ଯୋଉ ପ୍ରାକ୍ଟିକାଲ ଅଛି କୋର୍ସରେ ସେଥିରୁ 5ଟା 6ଟା ପ୍ରାକ୍ଟିକାଲ ହବ।
अच्छा ठीक ଅଛି କାହିଁକି ନା ମତେ ଏଇ ଗୁଡାକରେ ଇଣ୍ଟରେଷ୍ଟ କେବଳ ସେ ପ୍ରାକ୍ଟିକାଲ ପାଇଁ ମୁଁ ଆଡମିସନ କରିଛି
ଆଚ୍ଛା,
ଟିକେ
ସେ
ଏ ବିଷୟରେ
ଷ୍ଟଡି
ଜାଣିବାକୁ
ସେଣ୍ଟର କୋଉ ଷ୍ଟଡି ସେଣ୍ଟର କି?
ଆମର କିଟ୍ ସାର୍
ହଁ, ସେ ତ ସେଇ ଅନୁସାରେ କିଛି କିଛି ପ୍ରାକ୍ଟିକାଲ ହବ, ଯେତିକି ତମର ସିଲାବସରେ ଅଛି ଏଭ୍ରି ପେପରରେ 12-13ଟା ଅଛି ଏକ୍ସପେରିମେଣ୍ଟ, ତ
ଆଜ୍ଞା
ସେଥିରୁ 5ଟା 6ଟା
ଆଜ୍ଞା
ପ୍ରାକ୍ଟିକାଲ ହବ।
ଆଜ୍ଞା ଏ ଆଟମିକ ଆଜବେଷ୍ଟସ ସ୍ପେକ୍ଟ୍ରୋମିଟର ମୁଁ ସିପେଟ ରେ ୟୁଜ କରୁଛି ତ ସେଇଟା ଏକ ତେଣୁକରି
ଓହୋ
ଟିକେ
ହୋ,
ମତେ ଆଉ ଟିକେ
ତ କେମିଷ୍ଟ୍ରି ବ୍ୟାକଗ୍ରାଉଣ୍ଡ ନା କୋଉ ସବଜେକ୍ଟରେ?
ଆଜ୍ଞା ସାର୍ ମୁଁ ଅଲରେଡି ଏମଏସସି କରିସାରିଛି କେମିଷ୍ଟ୍ରିରେ
ଓକେ, ରାଇଟ।
ଆଜ୍ଞା
So
ଠିକ ଅଛି
initially, so initially the free atoms present in the sample will subjected to UV visible source, and after that the electrons present in the free atoms will undergo excitation, and they will emit electromagnetic radiation of a characteristic frequency. By analyzing that frequency, we can conclude that which atoms are present in the sample. First, the radiation is observed. That means the UV visible. So radiation is absorbed by the sample. Then the intensity of the radiation is attenuated. The observed radiation causes excitation of electron from the ground state to an excited level, and the electrons will go to which excited state, that depends upon the amount of energy absorbed in the UV visible source. The extent of absorption is a quantitative measure of the concentration of the atomic vapors of the element in the ground state. It is an electronic excitation, and the energy transition lies in the UV visible region of the electromagnetic spectrum. Now coming to the second one is atomic emission spectroscopy. So first it is atomic absorption spectroscopy, and the second one is atomic emission spectroscopy. In this method, a sample is normally excited by thermal energy. So that means here we will only analyze the emitted electromagnetic radiation, but initially the sample under investigation will be excited by thermal energy of a flame, of a flame, of a flame or argon plasma or electric discharge by any one of the thermal energy source. The initially the sample will undergo excitation, and the atoms present in the sample, absorb the thermal energy, causing excitation of the outer orbital electrons. As the excited state is very short-lived, then the excited atoms return back to the ground state after a very short time, typically around 10 to the power minus 6 to 10 to the power minus 9 seconds. This is accompanied by emission of electromagnetic radiation, and normally in the form of the light in the UV visible region. And the wavelength of the emitted radiation and its intensity provide the qualitative and quantitative information about the analyte. That means which atoms are present in the analyte and what are the concentration of corresponding element present in the analyte. That can be calculated. Now, the atomic emission spectroscopy employing flame as means of excitation, that is called flame photometry, or that is also called as flame emission spectroscopy. It is used for routine determination of metals mainly, and particularly this spectroscopy is applicable for alkali and alkaline earth metals, and similarly may other metals can also be analyzed. Now coming to atomic fluorescence spectroscopy, AFS. So in the AFS, the gaseous atoms are excited to higher energy level by absorption of the electromagnetic radiation, and the fluorescence emission from these excited atoms is measured. In the previous class, we have discussed about how the molecules present in the sample will first excited by absorbing electromagnetic radiation, and after that they will undergo fluorescence spectroscopy by different processes that may undergo fluorescence, that may undergo phosphorescence, etc. That we have discussed. But in today's, here the sample is in isolated gaseous atomic form. That means before the analysis, the sample should be the sample should undergo atomization by the various processes, and after atomization, the isolated gaseous atoms present in the sample will first excited by absorption of electromagnetic radiation, and after that they will undergo fluorescence emission. The main advantages of the fluorescence detection compared to absorption measurement is the greater sensitivity achievable because the fluorescence signal has a very low background of radiation. So that means if the concentration level of the atoms present in the analyte is extremely less, that can also be detected using this AFS technique. A schematic representation of the transition associated with the associated with the above three processes are given below. So the first one is figure A, that is the emission spectra. Sorry, the figure A is absorption spectra, the figure B is emission, and the figure C is fluorescence emission. So here first we will discuss the absorption spectra. Initially, the analyte present in the sample will be in the ground state, and after that they will absorb electromagnetic radiation of particular wavelength, and they will undergo excitation to some higher energy level, and the absorbed electromagnetic radiation can be analyzed, that will give the characteristics of the atoms present in the sample. And in the second one, that is the emission spectra. In emission spectra, initially the isolated gaseous atoms present in the sample will be excited by thermal technique, by any one of the thermal technique, for example by a flame, or by argon plasma, or by electric discharge, etc., so that they will undergo to excited state depending upon the amount of energy absorbed from the thermal technique. So they will move to that type of excited state, and after that they will undergo either de-excitation by that either non-radiative de-excitation, or they will undergo de-excitation by emitting electromagnetic radiation of a characteristics frequency, and analyzing that characteristics frequency we can say that which atoms present in the sample. And similarly, in the third technique, the isolated gaseous atoms present in the analyte will be excited by absorbing electromagnetic radiation. They will undergo excitation, and after that, depending upon the characteristics of the atoms present in the sample, they will undergo fluorescence. The fluorescence may be resonance fluorescence or that may be non-resonance fluorescence. If that will undergo resonance fluorescence, directly they will come back to the ground state, and for non-resonance fluorescence, they will be indirectly come back to the ground state. That will discuss in details in that corresponding portion. As we have a number of methods of atomization, because initially we have discussed about the different types of atomization techniques are there, and depending upon the different types of atomization techniques, the three different spectroscopic methods, that is the absorption, emission and fluorescence emission, absorption, emission and fluorescence emission spectroscopic methods of the measuring radiation analyte interaction, there are different types of atomic spectroscopic method. For example, if the atomic spectroscopic method is determined by both the method of atomization as well as the nature of the interaction, for example, the atomic spectroscopic method using electrothermal atomization method and studying the, so if the initial atomization technique will be electrothermal atomization method, and if we study the fluorescence emission spectroscopy, then that is called electrothermal atomic fluorescence spectroscopy. Now here 5 different atomization methods are there and 3 corresponding spectroscopic techniques are there. 3 corresponding atomic spectroscopic techniques are there, and hence total 15 number of different atomic spectroscopic methods are there. For example, in one question is there: identify the method of atomization and the type of radiation analyte interaction using the following atomic spectroscopic method. So here different atomic spectroscopic methods are there. There can be 15 possible atomic spectroscopic methods will be there. So the first one is flame atomic emission spectroscopy. That means the initial atomization technique will be flame, and the spectroscopic method will be atomic emission spectroscopy, AES. The analyte will undergo atomization by flame and the spectroscopic method will be AES. So that's why overall that is called flame atomic emission spectroscopy, FAES. Similarly, here the atomization technique is graphite furnace and the spectroscopic method is atomic absorption spectroscopy. So overall that is called a GFAAS. And similarly the third one, the atomization technique is inductively coupled plasma and the spectroscopic method is atomic absorption spectroscopy, AAS. That's why that is called ICP-AAS. And similarly in the fourth one, the atomization technique is flame and the spectroscopic method is atomic fluorescence spectroscopy, that is called FAFS. And similarly we can find out 15 different atomic spectroscopic techniques are there. Now coming to the characteristics of atomic spectrum. In the previous 6 modules we have discussed the molecular spectroscopic methods. For molecular spectroscopic methods, the peaks are generally broad peaks because these consist of a number of closely spaced lines containing what that is called energy band. So for molecule we can observe energy band that we have discussed in the previous 6 units. For molecule the electrons are present in different energy band. So that's why the corresponding energy band means a group of closely spaced lines constituting what that is called energy band, and the corresponding spectra will be band spectrum. That means for molecule we can observe band spectrum. But in case of the band nature of the spectrum is due to the number of factors like the quantization and the rotational vibrational motion of the molecule, along with the quantization of energy levels. In addition, the width of the spectrum is also dependent of the sum of the instrumental parameters. So this is about the molecular spectroscopic techniques what we have discussed in the previous 6 units. But in case of atomic spectra, for isolated gaseous atom or for individual atom, the atom consists of number of very sharp lines. That is the characteristics of the atomic species. It implies that this give rise to line spectra. So if we'll if we'll analyze the atomic spectroscopic methods, all the atomic spectroscopic methods will give line spectra. But for molecular spectroscopic techniques, they will give band spectra. The atomic spectra are generally much sharper because in case of because in atomic system the rotational and vibrational motions are not quantized and the transition are observed among the electronic energy levels of the observing species. Because for individual atom or for isolated atom, we cannot analyze the vibrational and rotational spectra. The vibrational and so rotational spectra can be analyzed only for molecules. But here we are discussing the different atomic spectroscopic techniques that is applicable for isolated or individual gaseous atoms. So isolated individual gaseous atoms are considered to be spherical in nature. So that's why the vibrational and we cannot analyze the vibrational and so rotational motion of the isolated individual spherical atom. But we can only analyze the transition of the electrons present in the atom in various energy levels. So here the electronic energy levels of the observing species can be analyzed. That's why the atomic spectra will give rise to line spectra which is very much sharper as comparison to molecular spectra. So here you can see one figure. In this figure it is given the representation of typical atomic spectra. Here it is given. We can analyze sharp peaks are obtained. And similar to molecular spectrum, the signals in an atomic spectrum are also characterized in terms of three parameters. They are position of the spectra, intensity of the spectra, and width of the peak. Position of the peak, intensity of the peak, width of the peak. So that's similar to molecular spectrum. So first we'll discuss about the position of the signal or position of the peak. The interaction in terms of absorption, emission or scattering of the radiation, in case of atomic species, the interaction cause transition among the different energy levels, only electronic energy levels, because as we have already discussed, for molecular species, the interaction can cause transition in various rotational energy levels, various vibrational energy levels, and also various electronic energy levels in case of molecules. But in case of atomic species, the interaction cause a transition among the electronic energy levels only. Whereas you have learned that in case of molecules, the interaction leads to transition among the rotational, vibrational, and electronic energy levels or combination of all these. However, like in case of molecular spectra, here also position of the spectral signal or the peak is determined by difference in the energy levels of the is determined by difference in the energy level of the different energy levels. So just like molecular spectra, here also we can find out the position of the peak or the position of the spectral signal by determining the energy difference where the electron will undergo transition from one energy level to another energy level. For example, if E2 and E1 represent the energy of the higher and lower energy levels concerned, then the energy change during transition from E2 to E1 energy level may be defined as like this. So here E2 and E1 represent the energy of the higher and lower energy levels. of a particular atom. And the energy change, if the atom will undergo emission spectra, then the excited electron from higher energy level E2 will come back to the lower energy level E1 by emitting electromagnetic radiation of a particular wavelength or frequency. And that particular wavelength or frequency can be calculated using the formula del E equals to E2 minus E1, which is equals to h nu, which is equals to hc by lambda. So we can easily calculate the frequency or wavelength of the emitted radiation by the atom. And similarly, lambda can be calculated by hc divided by del E. Here h is the Planck's constant, c is the velocity of light, nu is the frequency, and lambda is the wavelength of the emitted radiation. The wavelength of the emitted radiation is characteristics of the atom of the particular element from which it is emitted. So that means we can analyze the wavelength or frequency of the radiation, and from that wavelength or frequency value we can say that which atoms are present in the sample, because all the different atoms, all the different 118 atoms will give rise to emit electromagnetic radiation of different frequency or different wavelength. Now coming to, so this one is the position of the signal. So from the position of the signal we can find out the sample. So from position of the signal we can find out the frequency or wavelength of the emitted radiation from the sample, and from that we can know which atoms or which elements are present in the sample. So now coming to the second one, intensity of the signal. The intensity of signal depends upon the population of the energy levels from which the transition is originating and the probability of such type of transition. So intensity of signal will give rise to how many atoms, in how many atoms the electrons excited to which energy level, and from that energy level that will undergo emission and come back to the ground state. Because in the unit 1 we have already discussed, according to Boltzmann statistical distribution, the population of the ground state, that is the population means here the number of species present in the ground state. Suppose you will, if you will take 100 different atoms and they will be excited. So out of 100 different atoms, in how many atoms the electrons are present in ground state? That is called population. That is the number of species in the ground state is the highest, and it keeps on decreasing as we move to higher energy levels. So the population of the different atoms in the ground state will be highest, and if we calculate how many atoms are in first excited state, it will less than the number of atoms in the ground state, and if we calculate how many atoms present in the second excited state, it will still less than the number of atoms present in the first excited state, etc. It keeps on decreasing as we move to higher energy levels. In case of atoms, the population of any excited state relative to the ground state is given by this Boltzmann distribution formula, that Boltzmann statistical distribution that we have already discussed in unit 1, that is n star by n naught equals to g star by g naught into e to the power minus del E divided by kt. Or from this we can calculate n star equals to n naught into g star by g naught into e to the power minus del E by kt. Here n star and n naught are the number of atoms present in the excited state and in the ground state. That means n star is the number of atoms present in the excited state and n naught is the number of atoms present in the ground state. and del E is the energy difference between the ground and the excited state that is calculated in the unit of joule. G star and G naught are the statistical factors that depends upon the degeneracy of the energy levels involved. And K is the Boltzmann constant having the value 1.28 into 10 to the power minus 23 joule Kelvin inverse. And T equals to absolute temperature. So here one example is there. So from that example we can understand how many atoms or the population of the atoms present in the excited state and in the ground state, etc. The characteristics yellow emission of sodium vapor. So here it is given the sample contains sodium atoms in vapor phase and that will undergo yellow emission, that means emission of electromagnetic radiation in the visible region with yellow color. So the characteristics yellow emission of the sodium vapor contains a pair of lines at 589 nanometer and 589.6 nanometer. This one is the question. These arises from the emission of radiation by gaseous sodium atom in the 3p excited state to 3s ground state. Compute the ratio of the sodium atoms in the excited state to the ground state. So here the Boltzmann statistical distribution formula is n star divided by n naught equals to g star by g naught into e to the power minus del E by kt. Therefore, to evaluate the ratio of the atoms in the excited state to the ground state, we should know the statistical factors g star and g naught, and also we should know the value of the del E. As 3s and 3p energy levels have 2 and 6 quantum states. So for 3s energy level, 2 quantum states are there. For 3p energy level, 6 quantum states are there. So the statistical factors will be 2 and 6 for the value of G star and G naught. So that means for G star, the value will be 6. For G naught, it will be 2. So G star by G naught equals to 6 by 2, that is equals to 3. And the change in energy can be calculated by using the formula del E equals to Hc by lambda, because here lambda value is already given in the question. So del E equals to Planck's constant 6.626 into 10 to the power minus 34 joule second into c, that is velocity of light, that is 3 into 10 to the power 8 meter per second divided by lambda. So here it is taken, here it is considered the longer wavelength, that is 589.6 nanometer. But here it is so given 3, but that should be 589.6 nanometer. And here we have taken the value of Planck's constant as SI unit. So we should take the SI unit of wavelength, that is meter. So 589.3 into 589.3 nanometer can be written as 589.3 into 10 to the power minus 9 meter. And here we have taken the average of the two wavelength, that is 589.0 plus 589.6 divided by 2, that is 589.3 nanometer, which is to written as 589.3 into 10 to the power minus 9 meter. And from this value of the wavelength, we can calculate the energy difference between the 3s and 3p energy levels for sodium atom. And after that, we can substitute the values of del E and G star by G naught in the Boltzmann distribution, statistical distribution equation. So n star by n naught equals to 6 by 2. So 6 is G star, 2 is G naught. So that is 6 by 2 into e to the power minus del E. Del E value we have already calculated, and here it is given negative sign. Why negative sign? Because the electrons present in the sodium atom will undergo transition from 3p excited state to 3s ground state. That's why it will emit electromagnetic radiation within the visible region with yellow color. So that's why as the atom undergo emission by emitting yellow light, the energy of the system will be decreased. That's why a negative sign is there for del E. Here we have calculated del E equals to 3 into 3.37 into 10 to the power minus 19 joule. But whenever we will put the value in the Boltzmann equation, we have to put a negative sign because this is for emission of energy. And divided by K, the value of Boltzmann constant we should put, and finally in the equation del E by KT. So here T is given 3000 Kelvin. So that mentioned in the question. And hence we can calculate the value of n star by n naught by, because all the values are given, so we can calculate n star by n naught equals to 3.096 into 10 to the power minus 4. So the ratio of the atoms in the excited state and ground state will be 3.096 into 10 to the power minus 4. Now coming to the intensity concentration relationship. What is the relationship between the intensity of the spectra and concentration of the atoms or the analyte present in the sample? The intensity of the emitted radiation P is proportional to number of excited atoms n star present in the sample. That is, P is directly proportional to n star, or we can write P equals to some constant A into n star, where A is a proportionality constant. Again, from equation 7.1, we see that the number of atoms in the excited state n star at a given temperature is proportional to n naught, because from this equation 7.1, from this equation, n star is directly proportional to n naught. So from equation 7.1, we see that the number of atoms present in the excited state, that is n star, at a particular temperature is proportional to n naught. Therefore, we can write P equals to, here the in this equation P equals to proportionality constant A into n star. By putting the value of the n star, we can write P equals to A into, in place of n star, we can put these values, and at a particular temperature, if the temperature is constant, this factor is also constant. So we can, if the temperature will constant, this factor will also constant, and this is one proportionality constant. So we can write P equals to some overall constant K into n naught, where K equals to A into G star by G naught into e to the power minus del E by KT. And hence we can write P equals to K dash into C, because n star is n naught is directly proportional to the metal concentration. So what is n naught? N naught is the number of atoms present in the ground state, that is directly proportional to the number of metal atoms present in the sample. So that's why the intensity of the emission spectra, P is equals to some constant into concentration of the metals present in the sample. So that is, P is directly proportional to C. That means if more metal atoms will be there in the sample, then the intensity of the spectra will be more. Now coming to the next one, that is called spectral line width. The lines are generally symmetric around the lambda max. So here, if you consider this is a spectra, this is a peak, or this is a signal obtained by any type of sample. So from this signal, we can find out which, and in this graph, the x-axis is the wavelength, change in wavelength, and the y-axis will be observance or emitted power. If absorption spectra will be there, the y-axis will be observance, and if emission spectra will be there, the y-axis will be intensity, that is the emitting power. Emitting power means that is nothing but the intensity. For absorption spectra, the y-axis will be observance, and for emission spectra, the y-axis will be emitting power or intensity. So here a typical atomic signal is there. The signal may be atomic or emission spectra or from the absorption spectra. From this typical signal or peak, we can find out at which position of the wavelength the intensity will be maximum. The position of the wavelength, the intensity or observance will be maximum. That means at which position of lambda the y value will be maximum. That is called the corresponding lambda value is called lambda max. So this one called lambda max. The lines are generally symmetric around the lambda max. So if so, the middle one is so this one is the lambda max, and generally the peaks obtained that will symmetric around the lambda max, and the wavelength at which the intensity of emitted radiation is maximum or the observance will be maximum, then the corresponding wavelength is called a lambda max. So the observance is also maximum at the same wavelength. The line width is defined as the width of the signal measured at one half of the height of the maximum signal. So here, so this is a particular peak. If we will calculate the width of the peak, so here the width will be less, here the width will be more, and here the width will be still more. So at which position we will calculate the line width? So the line width can be calculated at a position that is called FWHM. That means at one half of the full wave half maximum. Full width half maximum. So the full width half maximum. That means we will calculate the height of the maximum height of the signal. So this is the maximum height, and half of the maximum height will calculate what is the width of the signal. That is called full width half maximum, FWHM. The line width is defined as width of the signal measured at one half of the height of the maximum signal. That means half of the height of the maximum signal. At that position, what will be the width of the signal? That is called FWHM, and that is considered as the width of the signal. It is expressed as del lambda half and is measured in the unit of wavelength, because so this one is the del lambda half or FWHM that can be measured according to the unit of the signal. This is full width. This full width is measured at one half of the maximum, that is called effective line width. So the effective width of the peak will be measured at this position, that is called FWHM. So the line width of the line width resulting from a transition of an electron between two discrete single value energy state is expected to be 0. So if only electronic transition will be there between two discrete energy levels, that means so these are the two discrete energy levels. Discrete means individual energy levels, and if the electron will undergo transition from lower to higher state, and again that will undergo emission from higher to lower state, then the corresponding so this will give rise to absorption spectra, and this will give rise to emission spectra. The corresponding absorption or emission spectra will be a very sharp line, and in that case the FWHM will be considered to be 0. If the transition leading to atomic spectrum are among the discrete energy levels, the FWHM will be considered to be 0 or negligible. So this finite and natural width of the atomic spectra result from the number of phenomena. But actually, theoretically, the width of the atomic spectra should be 0. But the existence of FWHM due to number of different parameters. So first one is uncertainty or Heisenberg broadening. These arises due to uncertainty in the energies of the excited state. So this is the cause of broadening. Theoretically, for atomic spectra, the line should be a very sharp line, but in practical case, line broadening will be there. So the first cause of broadening is uncertainty or Heisenberg broadening. Then the second broadening, that is called collisional broadening. It is due to distortion of the outer energy levels arising as a consequence of collision of one atom with other atoms. And the third one is Doppler broadening. It is due to shift of the frequency of the emitted photons due to relative motion with respect to detector. So these are the three causes of the broadening of the atomic spectra. But theoretically, the atomic spectra should be a sharp line with zero FWHM. But in practical case, we will find finite FWHM or natural width of a signal. So that is due to these three causes. Now coming to principle of flame photometry. So here we will discuss the principle of flame photometry. According to IPAC, the flame photometry is abbreviated as FAES, that is called flame atomic emission spectrometry. So first we will discuss. So here we will discuss the principle of flame photometry. First one is the fate of the sample in the flame. In a typical flame photometric experiment, a solution containing the relevant substance is to be analyzed. In a typical flame photometric experiment, a solution containing the relevant substance. So that means if you want to analyze the flame photometry of the substance should be first made up of the substance will be used in the form of solution with a suitable solvent, and the solution containing the relevant substance to be analyzed is aspirated into a burner and dispersed into the flame as a fine spray. That means the solution will be sprayed into a burner, into a burner, and then the solution will undergo dispersed into a flame to fine spray, and this process is called nebulization. So in the nebulization process, the sample undergo investigation on the flame photometry. Initially, that will be converted into a solution by using a suitable solvent, and after that, the solution will be respirated to the burner and dispersed into the flame as fine spray, and the process is called nebulization. In the flame, the solvent evaporates fast. The initially when the solution will be dispersed into a flame, so first the solvent present in the dispersed solution will evaporate fast. So when the solvent will be evaporated, only the sample will be there in the spray, and leaving finely divided solid particles which move to the hottest region of the frame where the gaseous atoms and ions are produced. So when the solvent molecules or when the solvent will be evaporated, then the substance will contain only solid particles, only finely divided solid particles, which will undergo investigation, and that finely divided solid particle move to the hottest zone of the flame where the finely divided solid particles will be converted into gaseous atoms or ions, and the atoms are excited by absorbing energy available from the flame. As the excited atoms return to the ground state of lower energy, then radiation of wavelength and characteristics of the element is emitted. So different element will emit electromagnetic radiation with different wavelength or frequency. The intensity of the emitted radiation is then measured, which can be related to the concentration of the element present, which forms the basis of the quantitative analysis. The initial one is the qualitative analysis. We can find out, we can analyze the wavelength of the emitted radiation, and that will give rise to which atoms present in the sample, that is qualitative analysis. And from the intensity of the emitted radiation, we can find out the quantitative analysis. The following processes occur in the flame. So in the flame photometry, following are the different steps. So first one is desolvation. the sample containing the metal particle is dehydrated by heat of the flame and the solvent is evaporated. Initially, suppose we will analyze the flame photometry of any alkali metal or alkaline earth metal. Initially, the metals will be dispersed in a particular solvent to form a solution, and when the solution will be aspirated, the solution will be nebulized to a flame, then in first the solvent will be vaporized, and after that only the finely divided solid particles will be there. So that step is called desolvation. The sample containing metal particles is dehydrated. That means that initially the when that will shown to the flame, the solvent will be evaporated. Initially, the metal particle is dehydrated by the heat of the flame, and the solvent is evaporated. Now coming to the second step, the heat of the flame vaporizes and the heat of the flame vaporizes the sample constituents. No chemical change takes place up to this stage. Now, after that, that will undergo atomization. At this stage, the metal ions, where the solvent has reduced to metal atoms. For example, if magnesium ions will be there, Mg2 plus, they will gain 2 electrons to form isolated magnesium gaseous atoms. By heat of the flame and the action of the reducing gas, that means the fuel, the molecules and ions of the sample species are decomposed and reduced to give neutral atoms. So that is called atomization. Now coming to the next step, that is called excitation. After converting to isolated gaseous atoms, the atoms at this stage are able to absorb energy from the heat of the flame, and the amount of energy absorbed depends upon the electrostatic forces of the attraction between the negatively charged electrons and the positively charged nucleus. So this is in turn depends upon the number of protons in the nucleus. As the electron absorb energy, they move to higher energy levels. What much amount of energy the atom has to absorb, that depends upon the electrostatic interaction between the nucleus and the electrons present in the atom. By absorbing greater than equals to that amount of energy, the electrons present in the ground state will excited to higher energy level or excited state, are then in the excited state. So here the 5 processes are there. So here, so the fifth process is when the electron will move from ground state to excited state. There after that, that will undergo emission of electromagnetic radiation. So the fifth step is emission of radiation. The electron in the excited state are very unstable and move back to the ground state or a lower state quickly, and they emit energy in the form of radiation of characteristic wavelength, which is measured by a detector. For some metal, this radiation corresponds to wavelength of the light in the visible region of the electromagnetic spectrum and is observed as a characteristic color. So as the wavelength of the emitted electromagnetic radiation falls in the visible region of the electromagnetic spectrum, so the emitted electromagnetic radiation looks like color. As the electrons from different energy levels are able to emit light, as they relax, the flame color observed will be a mixture of all the different wavelengths emitted by the different electrons in the metal atom under investigation, and give a block diagram represent. Here, so the diagram is there. So so these are the 5 steps. So here the 5 steps are summarized here. First one, we have to make a solution. Suppose Mx is a salt of the metal M. We have to make the solution of the salt Mx in a particular solvent. and when the solution will be nebulized to a flame, that will the solvent will be evaporated. So only we will find the solid finely divided solid salt particles, and after that, with the heat of the flame, the finely divided solid salt particles will be converted into vapor particles, and then the vapor salt particle will undergo decomposition to metal and non-metal. Suppose if you take sodium chloride, then that will undergo decomposition to gaseous sodium gaseous atom and chlorine gas. So NaCl will undergo decomposition to Na gas plus half Cl2 gas. So we will get here only the metal atoms in gaseous form, and after that the metal atoms in vapor state or gaseous state will absorb energy from the flame and they will move to excited state, that is called M star. So the M gaseous state, M in the ground state will excited to M star in the excited state. And in the excited state, the lifetime will be very less. Again, the electrons will come back to the ground state directly or indirectly by emitting electromagnetic radiation of a particular frequency, that is h nu. And a particular individual metal atoms will give individual frequency. To analyze the wavelength or frequency of the by analyzing the wavelength or frequency of the emitted radiation, we can find out which type of atoms present in the solution. And similarly, by analyzing the intensity of the emission spectra, we can also quantitatively determine the concentration of the metal atoms or ions present in the sample. So this is the schematic diagram of the flame photometric method. So the flame photometric method, first we will make a salt solution of, by using a particular solvent, and after that the salt solution will be injected to a nebulizer. So then that will undergo nebulization. So that will be sprayed into the flame. So this is the process of the inside the flame, and during the spray or aspirate during the aspiration, the solvent will be removed, that is called desolvation process. And after removal of the solvent, that will convert it into solid or gas aerosol, and after that volatilization, they will be converted into gaseous molecules, and after that dissociation, they will be converted into gaseous atoms, and after that ionization, that will give rise to atomic ions, and again that will atomic ions, that is called excited ions, and after that that will undergo emission. The flame emission spectrums of the element of sodium can be obtained by replacing suppose we want to undergo we want to do flame emission spectrum of sodium. So the flame emission spectrum of the element of sodium can be obtained by placing a solution of sodium chloride in a suitable flame at a temperature of the flame. The temperature of the flame should be 2000 degrees Celsius to 3000 degrees Celsius, and the outer electrons of the sodium. So in the presence of this extremely high temperature, all the solvent molecules will be desolvated. After that, the sodium chloride solid particle will be vaporized to sodium chloride gaseous particle. Then that will undergo decomposition to isolated gaseous sodium atoms and chlorine gas. The chlorine gas will be removed. Then the individual sodium atom will absorb energy from the flame, and the electrons present in the sodium atom will undergo excitation. And the outer electron of the sodium atom is promoted, that means that will undergo excitation from the ground state. First, the outer electron will undergo excitation. So the outer electron of the sodium atom will present in the 3s orbital, that will excite into different p orbitals. So the electrons present in the gaseous sodium atom at the 3s orbital will excite to 3p or 4p or 5p orbital depending upon the amount of energy absorbed from the flame. And after that, that will undergo relaxation. The relaxation of the excited electron gives rise to characteristic emission spectrum of the sodium atom. The emission spectrum of the sodium atom is relatively simple and containing about 40 signals or lines. The most prominent signals being the region at 285 nanometer, 330 nanometer, and 590 nanometer. The figure shows a portion of the flame emission spectrum of sodium atom, and the excitation is being done by oxyhydrogen flame. So here the flame is oxyhydrogen flame. So initially the sodium chloride salt solution will undergo will undergo nebulization and desolvation, then decomposition, then vaporization, and after that the isolated gaseous sodium atom will undergo excitation by oxyhydrogen flame, and after excitation the sodium atoms will emit emission spectra. So this is a characteristic emission spectra obtained in sodium atom, and here you can see the peaks are at a position of 589 and 589.6 nanometer, and another peak will be observed at the point 566.3 and 568.8 nanometer. You can observe an intense signal at 589 nanometer in the emission of the sodium atom. This is This in fact consists a pair of lines. Apart from that, that will contain a pair of lines at 589 nanometer and 589.6 nanometer, which would not be resolved due to instrumental limitation. So that cannot be separated due to instrumental limitation. So the pair of lines originate from the relaxation of the excited electron in the 3p to 3s level and is responsible for the characteristics yellow glow of the sodium light. So this type of emission spectra at 589 nanometer and 589.6 nanometer arises due to emission of the excited electron, due to transition of the excited electron from the 3s energy level, from the 3p energy level, again that will come back to the 3s energy level. So due to that, the emitted radiation having wavelength in the range of 589.3 nanometer, 589 to 589.6 nanometer. That's why the emitted electromagnetic radiation will looks like yellow color. So here, this is the energy level diagram for sodium atom. We know that the sodium atom, the outermost electron in the sodium atom will present at 3s energy level. So if that can absorb energy from the oxyhydrogen flame, that can absorb energy from the flame, and by absorbing energy, the outer electron present in the sodium atom at 3s energy level can excite either from 3s to 3p. So here you can see that can excite either from that can excite either from 3s to 3p, 3s to 3p, or from 3s to 4p, or from 3s to 5p, depending upon the amount of energy absorbed. And again, and the population of the transition from 3s to 3p will be maximum, because there is a higher probability of transition of electron from 3s energy level to 3p energy level for most of the atoms, right? And after that, the electron present in the excited state, that is the electron present in the 3s energy level, will undergo relaxation by coming back from 3p energy level again to 3s energy level by emitting radiation at 589 nanometer and or 589.6 nanometer. So these are the two different peaks obtained. That means you can see, so these are yellow color electromagnetic radiations are there. As you have learned above, in case of atomic emission spectroscopy, The intensity of the emission signal depends upon the number of atoms in the excited state. In case of sodium atom, the ground state is 3s ground state. According to term symbol, the 3s ground state can be written as 2s half, and the excited state is 3p excited state, or 4p, or 4, the excited states are 3p excited states, or 3D excited state, or 4s excited state, or 4p excited state, or 5s 5p excited states. So the intensity of the emission when the excited atoms return to the ground state will be maximum from the first excited state. So the two lines will be yellow color. So that will emit electromagnetic radiation of yellow color. So that means the maximum probability that the electrons of the isolated sodium gaseous atom will undergo excitation from 3s to 3p, and again they will come back from 3p to ground state. In case of sodium atom, the 2p 3 half, the 2p 3 by 2 and 2p 1 by 2 states would be the most populated transition in this state. So you can see this one is this one is the 3p state. So in the 3p energy level, two states are there. One state is 2p 3 by 2, and another term of the state is 2p 1 by 2. So from these two microstates, these two microstates will present in the 3p energy level. From these two microstates, the electron will come back to 3s energy level. That's why that will give rise to electromagnetic radiation with two different wavelengths. First one is 589.0 and the second one is 589.6 nanometer. So the intensity of the emission when the excited atoms return to the ground state will be maximum from the first excited state, that is from the 3p excited state. The 3p excited state contains two microstates according to the term symbol 2p 3 by 2 and 2p 1 by 2, and after that they will come back from 2p 3 by 2 to 3s, and from 2p 1 by 2 to 3s. So that's why the sodium atom will show two signals, one signal at 589 nanometer and another signal at 589.6 nanometer. So as in case of sodium, the 2p 3 by 2 and 2p 1 by 2 states would be most populated, and transition from this state to the ground state is allowed. Transition from this state to the ground state is allowed because the selection rule for transition is del S should be equals to 0 and del L should be equals to plus minus 1, and the intensity of emission from this state would be maximum, and the fraction of atoms in the excited state of different element of various temperature is presented in the table 7.1. The data shows that nearly all atoms will be present in the ground state. So here if we will observe the flame photometry of sodium atom, the emission line will obtain at 589. If the temperature of the flame will be 2000 degrees Celsius, 2000 Kelvin, the fraction of atoms in the excited state at different energy level is 1 into 10 to the power minus 5. And if the temperature will increase from 2000 Kelvin to 3000 Kelvin, the fraction of atoms will increase. The fraction of atoms will increase by 60 times. And if the temperature will again increase, the fraction of atoms will be increased by 400 times. The fraction of atoms undergo excitation will be increased by 400 times. And similarly for potassium atom, the emission line will be observed at 767 nanometer. For lithium atom, the emission line will be observed at 670. For calcium atom, the emission line will be found at 422. For magnesium atom, it will be observed at 285. And then we'll discuss flame and its characteristics. So in the flame photometric technique, here we will discuss the flame and the characteristics of the flame. So just we will take 2 minutes gap, and after that again we will start. Okay, we will start from here. Flame and its characteristics. A flame can be described as a steady state gas phase reaction which takes place with emission of light. A flame can be described as a steady state gas phase reaction which takes place with emission of light. It is produced by burning of mixture of a fuel with air or with any other type of oxidant in a burner. In flame photometry, a variety of fuels can be used. Generally, air, oxygen, and nitrous oxide is used as the oxidant. Various types of fuels can be used. and the fuel will undergo combustion in presence of air, oxygen or nitrous oxide as oxidant. The flame temperature depends upon the fuel oxidant ratio. Combination of given fuel gas and air produces lower temperature as compared to when O2 is used as oxidant. Alkali and alkaline earth metals are easily excited at lower temperature obtained by using air. However, if we consider heavy metals, oxygen and nitrous oxide as employed as the oxidant. If we analyze the sample of alkali or alkaline earth metal, they can be easily excited with air as fuel. But if you want to analyze heavy metal atoms, then oxygen or nitrous oxide can be used as can be employed. Then oxygen and nitrous oxide as employed as oxidant. This requisite temperature for analysis can be obtained by varying the fuel oxidant ratio. The table 7.2 lists some common fuel and oxidant along with the range of temperature attained using them. So the first one is if the fuel will be propane, if you will use propane fuel and air will be the oxidant, then the temperature produced will be 2250. And in case of propane fuel, if oxygen will be the oxidant, then the temperature will be 3070 degrees Celsius. And similarly for acetylene fuel, if the oxidant will be air, it will produce 2470, and if the oxidant will be oxygen, that will produce 3320, and if the oxidant will be nitrous oxide, that will produce 3220. And similarly, if the fuel is hydrogen and the oxidant is air, that will produce 2370 temperature, and if oxygen will be the oxidant, then that will produce 3050 degrees Celsius. The most commonly employed flame in the flame photometry can be grouped into two types. The flame in which the fuel and oxidant as air or oxygen as well as mixing before combustion. So that is called pre-mix or laminar flames. So the two types of flames are there. The first one is the flame in which the fuel and oxidant are well mixed before combustion process. So before combustion, the fuel and oxidant are well mixed, and that is called a premix or laminar flame. And in the second type, flames in which the fuel gas and the oxidant are mixed in the flame itself. So here mixing will take place in the flame itself, that is called on premix or turbulent flame. Now coming to the structure of flame. So the flame contains two different zones, that is called secondary reaction zone and primary reaction zone. The flame are not uniform in combustion, length or cross section. The structure of a pre-mix flame or a laminar flame is given here. So this is the structure of a laminar flame. So the flame contains different zones. So the first, so the flame, the following zones or following, so regions are there. The regions of the flame, the first one is preheating zone. So this one is the preheating zone where the temperature will be less. And the second one is primary reaction zone or inner zone. So this one is the primary reaction zone, that is blue color zone, that is the primary reaction zone. Then internal zone, and the last one is secondary reaction zone. So now coming to the different zones, what are the characteristics of the different zones? The first or innermost region of the flame is called preheating zone, where the combustion mixture is heated in the ignition temperature by thermal conduction from primary reaction zone. The second zone is the primary reaction zone and the inner zone. The zone is about 0.1 mm thickness at atmospheric pressure and is visible by virtue of blue green light ascribing due to the formation of the C2 free radical and CH free radical. There is no thermodynamic equilibrium in this zone, and the concentration of the ions and free radicals is very high. The region is not used for flame photometry. So that means the primary reaction zone or inner zone and the preheating zone, these regions, these two regions, preheating zone and primary reaction zone. So these two regions are not used for flame photometry. and immediately above the primary reaction zone, that is the third zone, that is called interconal zone or the reaction free zone, which can extend up to a considerable height, and the maximum temperature is achieved just above the T of the inner zone, just above the tip of the inner zone. So that is the interconal zone, and the height of the interconal zone will be maximum. So there will be maximum temperature will be observed in this zone. Immediately above the primary reaction zone, the third or interconal zone of the reaction, or that is called the reaction free zone, which can extend up to considerable height, and the maximum temperature is achieved just above the tip of the inner. That means when the inner zone will just complete, that region contains the maximum temperature, and the higher temperature favors both the production of free atoms and the maximum excitation of atomic emission spectroscopy. Therefore, the zone is used for flame photometry. That means these zones will be used for flame photometry. Just above the tip of the inner zone, these zones will be used for flame photometry. And the outermost, that is the fourth zone, that is called secondary reaction zone. Within this zone, the product of the combustible processes are burned to stable molecular species by the surrounding air. Now coming to the reactions in flame, first one is dissociation of the molecule. Mx will undergo dissociation in the flame to M and X, and here the rate of dissociation Kmx equals to Pm into Px divided by Pmx. The next one is formation of a compound with the flame component. The isolated gaseous atom or the individual gaseous atom will react with the flame component to form a compound. The reaction is M plus Y. Here M is the gaseous metallic atom that will react with the flame component Y to form My, and the rate of the reaction Kmy equals to Pm into Py divided by Pmy. And after that, ionization of atom will take place. The isolated gaseous atom or individual gaseous atom M will undergo ionization by excitation of electron from the ground state to excited state by absorbing energy from the flame, and that will converted into M plus E minus. In this equation, P is the partial pressure of the species indicated in the subscript, and the partial pressure of the flame gas component is much larger than the partial pressure of the given element. So here that is the partial pressure of the Py is the partial pressure of the flame gas. It is therefore considered constant and included into the equilibrium constant. The most important flame gas component forming compounds with the element are oxygen, hydroxyl radicals, and hydrogen. The most common compound formed in the flame burning with air or oxygen and metal monoxide. For example, a major fraction of alkaline earth metal is present as monoxide unless uh, very fuel rich flames are used. However, alkali metals practically do not form any oxides. Hydroxide species are present in some alkali and alkaline earth metals in the hydrocarbon flames. Then sodium forms practically no hydroxide. While the concentration of lithium hydroxide molecule often exceeded the atomic lithium concentration by a factor of 10, none of the alkali metal hydroxide emit spectral band in the visible or UV region. Whereas the spectral band of alkali and alkaline earth metal monohydroxide can be used in the determination of these elements. Now coming to instrumentation of a flame photometry. The flame photometry the sample is introduced into a flame where it undergoes number of processes leading to the formation and excitation of atomic species which emit radiation. The radiation is then measured and suitably analyzed. The instrument used for this purpose is that is called flame photometer. So the first one is flame atomizer. It converts the sample into excited atomic species and consists of the following. The flame atomizer contains a nebulizer and atomizer burner. The nebulizer and mixing chamber, it means of transporting a homogeneous solution into the flame at the steady rate. Then atomizer burner. Here the fuel and oxidant burns to give the flame that can be maintained at a constant form at a constant temperature. Now coming to the next one is filter or monochromator. It isolates the light of the wavelength to be measured from that of the extraneous emission. Then detector, it helps measuring the intensity of the radiation emitted by the flame. Then amplifier and readout device, it is used to amplify the signal provided by the suitable output. So here you can see this is the schematic diagram of a flame photometer. So in this schematic diagram of the flame photometer, you can see this is the nebulizer where the solution containing the metal salt will be aspirated to the flame. So this is the nebulizer, and this one is the burner. That means inside the burner nebulizer will be there, and the salt solution of the metal, the metal salt solution will be aspirated through this mixing chamber and through this nebulizer. And here some fuel gas is there and oxidant gas is there that will be aspirated to the flame, and in the third zone the reaction will take place, and after that will undergo emission spectra. Then the emitted electromagnetic radiation will pass through the monochromator or filter to give electromagnetic radiation of particular wavelength, and after that will be analyzed through the photodetector and the amplifier and readout device. So here we will discuss the different components of a flame photometer. First one is flame atomizer. The role of atomizer to generate vapors of the analyte which get excited by the thermal energy of the flame and then emit characteristics radiation that is measured. The flame atomizer assembly consists two components. The prior is a nebulizer where the sample is in the form of solution is drawn and converted into a fine aerosol. It is then passed into second component. The second component contains a burner along with oxygen or air or as fuel gas. In the flame, the number of processes occur that is converted into that convert the analyte into excited species. So here first one is nebulizer. Nebulizer is a device used for sample introduction into the flame, and the process is called nebulization that consists of thermal vaporization and dissociation of aerosol particles at high temperature, introducing a small particle size and high residence time. The number of nebulization methods are available. Large number of nebulization methods are available. So few are given. So that is pneumatic nebulization, ultrasonic nebulization, electrothermal nebulization, and hydride generation. So here in the pneumatic nebulization, that is most commonly used nebulization for introducing aqueous liquid sample. If aqueous liquid sample is there, that means if water will be used as a solvent for the particular metal salt, then the nebulization process will be pneumatic nebulization. In this technique, the sample solution is fed or aspirated into the nebulizer, which convert the liquid into fine mist or aerosol, which is then fed into the flame. A common type of pneumatic nebulizer is concentric pneumatic nebulizer as shown in the figure. So that is here this is a concentric nebulizer. Here the liquid input will be there. The liquid containing the analyte salt input will be there, that will be passed into the nebulizer, and here gas input will be there, that means the oxidant gas will be input here, that will, and after that will aspirated through the nozzle to the flame. So this one will present inside the burner at this position. So that is the nebulization position. Then coming to atomizer burner, the sample is introduced in the form of fine spray at a control rate into the flame of a burner with the help of nebulizer. In the nebulizer, the analyte undergoes a number of processes as mentioned earlier already, that we have discussed. Two types of atomic burners have been used in the flame photometry, that is pre-mix burner and total composition burner. First we'll discuss about the pre-mix burner. In the pre-mix burner, the fuel and oxidant are thoroughly mixed inside the burner inside the burner housing before they leave the burner portion, the burner pores and entry into the primary combustion or inner zone of the flame. Now, in this type of burner, the solution of the analyte is aspirated with the help of nebulizer from the sample container into the mixing chamber in which the fuel gas is also introduced. That means toward the nebulizer, the fuel gas is also introduced and simultaneously that will undergo aspiration. Then large drops are stubble by baffles in the mixing chamber and are drained out. Pressure and density fluctuation of the aerosol due to atomization are smoothened in the mixing chamber and the mixing aerosol. The fuel gas and oxidant bond to yield stable noiseless flame. Now coming to the solvent of the smaller droplets evaporate partly first in the mixing chamber, then it conduct the burner and finally into the flame. So this is the schematic diagram of a premix burner, and similarly other types of another burner is there, that is called total consumption burner. So in the total consumption burner, a total consumption burner combines the function of nebulizer and burner. So here the premix burner only acts as a nebulizer and burner will be in separate form, but in total consumption burner combines with the function of nebulizer and burner itself. So the burner itself is a nebulizer and burner. In this type of burner, the suction created by compression of oxidant streaming part of the, so this one is the total combustion burner. So here this is the analyte solution. So simultaneously nebulizer and burner. So it is a single part that contains both nebulizer and burner. In the total combustion burner has the following advantages. There is no losses of condensation or spray. That means no spray will be lost, because so this is a single part that will take the spray. All the materials enters into the flame. For this reason, the emission of a given concentration of analyte in the solution is higher than that of the premix flame. So no fractionation of the sample takes place during aspiration, and it eliminates error due to loss of non-volatile component. Combustible sample like petroleum can be directly aspirated into the flame without any danger or explosion. So these are the advantages. However, total consumption burners suffer from the following disadvantages. So these are the different disadvantages of the total combustion burner. Then droplets of the different disadvantages are droplets of the widely varying size is formed during the aspiration. Many of the large droplets are frequently blown right through the flame without totally evaporation and without pyrolysis of the solute. The flame is more stronger cooled by heavier load of the liquid. The burner tip can become incrusted with the salts. So that means salt solution will be there. So there is a chance of the blockage of the burner tips. The burners are very noisy, both physically and electronically, which leads to poor reproducibility of the analytical result. Then coming to the monochromator, the function of the monochromator after undergo the emission spectra, the function of the monochromator is to eliminate out to eliminate the unnecessary electromagnetic radiation, and only that will allow to pass the emitted radiation from the metal. Now coming to the detector. So the function of the detector is to measure the intensity of the radiation falling out from the monochromator. The different types of detectors are there. The two types of detectors, that is photoemissive cells or photomultiplier tubes, are commonly employed for this purpose. The detectors are also used in UV visible spectrophotometer. Now coming to amplifier and readout device, the output of the detector is suitably amplified and displaced in a readout device like a meter or a digital display. The sensitivity of the amplifier can change so as to able to analyze the sample in varying concentrations. Now coming to application of flame photometry. First one is in order to all the things we have already discussed. So here we will measure the qualitative application. Flame photometric methods are widely used in determination of concentration of alkali and alkaline earth metals in the sample that are easily prepared by aqueous solution. Some other element can also be detected visually by the color in the flame, that is sodium produces yellow flame. However, this method is not very reliable. The best method is to use flame photometer with filter and monochromator. That means in some cases we can also detect the qualitative analyze the presence of a sample by the color, but that is not a reliable method. That's why the best way to use a flame photometer with a monochromator and separate the radiation of the unnecessary electromagnetic radiations that can be separated by using a monochromator. Then coming to quantitative analysis, the concentration of the various alkali and alkaline earth metals is important in determining suitability of the soil for cultivation. Determining the suitability of the soil for cultivation, very often an analysis sets leaves the plant for K plus and Ca2 plus is carried out. This gives the idea of the concentration of these ions in the soil, which can taken up by the plant for agricultural purpose. An analysis of proper mixing of the surface soil and the subsoils is carried out to determine the fertilization requirement of the soil. In all these analysis, the soil and the ash is evaporated and dryness with concentrated hydrochloric acid, and the residue is treated with water or diluted hydrochloric acid to get the ions into the aqueous solution. And similarly, it has the application in clinical chemistry for analysis of sodium or potassium ion in body fluid, since their ratio controls the action of muscle, including the heart. And similarly, internal standard lithium is added to take care of mixing effect. For example, calcium analysis. In the calcium analysis, the La3 plus or EDTA must be added to the solution to avoid interference due to phosphate ion. So in the calcium analysis, due to as there is a chance of presence of some phosphate ion, so that can be eliminated by adding La3 plus or EDTA. Food and drinks are usually analyzed by ashing and leaching out of the ash with mineral acid to leach out the elements. Soft drinks, fruit juice, and alcoholic beverages can sometimes be analyzed using flame photometer. So here, the different element and the characteristics emission wavelength and the detection limit. So aluminum, the characteristics emission, so that will produce two characteristics emission spectra with the detection limit is 0.5 microgram, and for this 0.5 microgram. Similarly for, so these are the different elements are there and the corresponding wavelength and the detection limits are given here. Then coming to methodology for quantitative analysis, in order to determine the concentration of a particular metal present in the solution, first you have to take 5 different known concentration solution, and using that 5 different known concentration solution, then calibration will be done. Suppose we will take 5 different known concentrated solution. Using the 5 different known concentrated solution, a calibration curve will be done, and after that we will analyze the unknown solution for which we want to determine the concentration of the metal present in the solution. And here these are the suppose the unknown, the emission intensity of the unknown solution is this one, and we will put a horizontal line parallel to the x-axis, and the position at which it will cross the calibration curve, we will draw a vertical from that curve, and that will give rise to the concentration of the unknown solution. So by this method, we can analyze the concentration of the metals present in the analyte, and both qualitative and quantitative analysis can be done. So today we'll stop here. In the next class, we'll again, in the next class, we'll discuss the next unit. Okay.